Sounds good. We're going to get started right on time. Thanks, everybody, for being prompt and getting us back on time. So my name is Eleanor Sterling, as you might have heard before, and I'm the Chief Conservation Scientist at the American Museum of Natural History's Center for Biodiversity and Conservation, and I moonlight here teaching with my buddy Sharon. And today we have an amazing panel, and one of the reasons why we brought this panel together is a series of courses that Sharon and others and I are teaching. We're really trying to revamp the whole thing to be about food systems and to make all these connections. And we're desperately trying to figure out what tools do we use to help students better understand food systems. And we recognize that there's a pretty big set of opportunities from very, hand-drawn connections to fairly sophisticated computer models and computer programs. And so we thought we would pull together the angst that we've been having onto a panel of experts who can help us think through across a wide spectrum of low-tech, can I say, to high-tech opportunities for tools. And we're also very, very interested in how do we know if the students are learning these systems these systems thinking strategies, and are they able to transmit that from our classroom to further thinking in systems as they leave the classroom. And so really assessment is a major issue, and these folks are all thinking about that as they're developing their tools. And so I think the idea of what tool can I use to help students understand systems, and then how do I know that they learned it and can convert that learning to action in other areas is really fundamental. And so we're going to cover that today. I'm going to let these folks introduce themselves because I promised to keep the intro really short. So here we go. Yeah, here you go.
Okay. Hi, I'm Tammy Long. I'm at Michigan State University. I'm not in food systems, but I have a PhD in plant biology, so that's where my training comes from. I consider myself now a discipline-based education researcher, which means that in the last 10 years, my research has focused exclusively on learning and cognition in biology. So I'm in the Department of Plant Biology at MSU, and they have made a coordinated effort to have discipline-based education researchers in several of their major departments. So I also work with chemists and physicists and folks in the College of Ed, as well as my plant biology colleagues.
I'm Rebecca Jordan. I'm at Rutgers University. I'm in the departments of human ecology and ecology, evolution, natural resources. I'm a behavioral biologist, and I have spent the last 10 years or so researching how it is people reason with data.
And I'm Stephen Gray, and I'm from Michigan State University in the Department of Community Sustainability. My background is in kind of conservation biology and ecology, but I'm a systems modeler and primarily a participatory systems modeler. So how do we build tools where people can get together and kind of represent their understanding of these complex systems?
Does this comes with me, right? Yes. Okay. And let me know, can you guys hear me okay at this distance? And, okay, excellent. So I'm going to kick us off, and the progression from my talk to Rebecca's and then to Stephen's will be in order of increasing sophistication and reliance on technology in terms of the model itself. So I'm going to start, though, by first outlining what it is that we envision that we're contributing to the discussion today, or that we hope to contribute. So we'd like to have these things in mind as we go through. Our panel represents many different types of approaches to fostering and measuring systems thinking. So some of us will use the terminology of systems thinking explicitly, and others of us will talk about different facets of cognition or thinking and learning. We want you to be thinking about how it is that the approaches and tools are not necessarily rule-bound, but are very flexible. And so we encourage you to think about how you might appropriate the tools and approaches and technologies that we'll talk about today for your own purposes, because the idea is, of course, to adapt and make specific to meet your own unique needs. There are common considerations throughout systems thinking that we should be considering, and so we encourage you to challenge us on those if those do not come across clearly, and to also be considering trade-offs. So there are trade-offs, of course, associated with doing a very low to no tech approach, pen and paper type modeling, versus Rebecca's and Stephen's reliance on technological tools, as well as different communities of engagement to create and construct these models. So be thinking about how all of this works within the context of your unique needs, and we'll be happy to discuss all of that with you at the end. Would you guys like to add anything to this opener? Okay. All right, so I'm going to begin first by telling you about how I got into the research of looking at students thinking through model-based representations. And our work at MSU, I work with a team of colleagues that are distributed both at MSU as well as at North Dakota, Bethel University, and St. Louis University. And our work began in 2007, 2008, when we were undergoing a curricular renovation in our introductory biology program. So modeling wasn't necessarily at the forefront of our thinking at the time, but what we were trying to instill and what the jargon was that was circulating in biology education at that moment was thinking about active learning and thinking about becoming more student-centered in our approaches. So those were kind of the overall objectives that we were aiming for. But our way of incarnating those into something that was practicable and that was measurable was, first of all, I really don't like the term active learning because I think it's kind of an empty term that now has no meaning associated with it, so I tend not to use it. So our interpretation of what that was to mean for us at the time was to engage students in the authentic practices that biologists use in their own work. So the idea is to get students to learn biology by having them do the things that biologists do. And of course, when you're teaching in a classroom, this is my classroom, there are 500 students in there. You can't do things like have everybody at a microscope and a set of petri dishes. So you have to think a little bit more creatively about how you're going to accomplish that in that context. So the kinds of practices that we were thinking about in this redesign included things like building and using models, engaging in scientific argumentation, and analyzing complex data. So those are the core constructs that we were focusing on as our activities and our assessments, and then we had students interacting with those constructs in a variety of ways, having them use models or arguments that are presented to them, having them construct their own, having them evaluate, defend, revise, and share those kinds of artifacts with one another. Now, fortunately for us, later documents that came out beginning in 2011 and 2013, things like Next Generation Science Standards and Vision and Change, which are kind of the guiding documents and the things that we defer to now when we're thinking about what's happening in bioed nationally, those kinds of approaches align very nicely with those documents. So in all of these places, modeling and thinking about systems is emerging as a core theme throughout. So we were fortunate that the 50 years of data that led to these, that preceded it, were very consistent, and so we were not off the mark when these guiding documents came out. We found that we had a very nice fit there. So I want to talk specifically about how we've used modeling and how we're thinking about modeling in the undergraduate classroom. And we weren't necessarily thinking about engaging students in systems thinking at the time that we incorporated modeling in our classroom redesign. We were thinking about practical solutions to problems that we had and how to better engage students in understanding core concepts within the content that we were accountable for teaching. So we had specific instructionally based objectives that were driving our use of models. So first and foremost, the thing that we were after with models is engaging students in making connections among the core content that we were teaching in this class. I teach the second semester of an intro bio series for majors. So our content domains include genetics, ecology, and evolution. And what we were finding over and over again is that we would spend a lot of time on making sure students understood in a coherent way genetics concepts, and then we progressed to evolution and they purge their memory of everything that they've ever learned about genetics and think that evolution is something entirely different. When in fact what we really wanted is we wanted them to use genetics to explain evolution, because they are one and the same. And then when we get to ecology, use that prior information to understand the nature of interactions and how selection works in a system. So that was a primary goal for including modeling, is to help students visualize and see how these things are connected. A second practical goal was that we wanted to promote those skills. We wanted to promote students' ability to use and create models to facilitate their own thinking, because biologists do that all the time. Biologists regularly sketch out a diagram to help explain it to someone else and to actually evaluate their own thinking. We wanted students to be doing the same. And then finally, and this is not insignificant, we committed ourselves to not using multiple choice as our primary mode of assessment. And in fact, in my sections of my classes, you will not find a single multiple choice question on any of my exams. My class sizes have come down significantly to 250, but I'm very committed to the idea that we have to get students to represent their thinking in different ways. And if you've spent time grading students' papers and exam writing, you know that there's a lot of issues that go into making judgments about what students know and what they're thinking based on their writing. Because what seems like a lovely explanation in the first sentence suddenly becomes a profound misconception in the second. So we were finding that the models were actually really helping us to force the students to streamline their thinking and get rid of some of this extraneous explanation that wasn't helping them, and help us to better understand, we think, understanding what the students are thinking. However, when we actually implemented this into the classroom, we were both amazed and befuddled because we were seeing all kinds of things in our students' products that we had not experienced before. So both in terms of conceptual correctness and wrongness, as well as the diversity of ways that students were representing their ideas. So what that forced upon us in that moment is to try to find some kind of common standard or some kind of common framework so that we could make a reasonable comparison among students and at different points in time about the systems that they were modeling. So you'll notice that the approaches that I have here are quite different. We have basically a drawing with very little explanation here, contrasted with a structure that has quite a bit of explanation, and everything in between. So it was really hard to compare one student's representation to another. So our initial research, when we became fascinated with this way of thinking from our students, our early phase research was focused on trying to find a way to standardize and implement a framework that would allow us to standardize across students so that we could make meaningful comparisons. We wanted to be able to document differences within students at different points in time, among different student groups, across concepts, and also to evaluate the quality of the information that was represented. So that was our goal. It led us eventually to finding a framework that was articulated in the engineering literature. So in fact, from artificial intelligence, there's a theory that's called structure behavior function theory, and it's used to explain the constituent components of design systems. It comes from design system engineers, and it's intended to explain the different constituent components of systems that can be represented through models. So that's the way that we're thinking about this here. It's very simplistic. So it says that models and systems have three constituent components. First of all, there are things called structures. Those are the components of the system. These are the things that you're seeing in this particular diagram that are included in boxes. These are objects that interact in the system. Secondly, the engineers call these behaviors. Rebecca is going to take a little bit of time and talk about the problems associated with some of the language, that the engineering language is structure, behavior, function, but if you're a biologist, all of those things mean something quite different in context, so we often adapt the language appropriately. Engineers call these behaviors, we call them relationships, and ideally, relationships ought to be mechanistic kinds of relationships between structures in a system. And then finally, if you consider all of the aggregate components and their interactions, this system as a whole does something. And your model of that system tells a story. It has an explanation associated with it. We call that function. So the function is, what is the system doing and what is your model explaining? The last piece that we attach some definition to for the purposes of our research and for instruction is we consider the smallest unit of analysis within a student's model a proposition. And a proposition consists of two components and its relationship. So when students are building these models, we tell them that one of the rules is that the propositions have to have an autonomous meaning. So you can take a proposition out of a model and it has a meaning on its own. It doesn't need the rest of the model in order to, it doesn't have to rely on the rest of the model to explain what's happening between those two components. Does that make sense? So it's a very simple framework. And usually when I explain what our framework is, people say, oh, you're doing concept mapping. And I say, no, we're not. We're really not doing concept mapping. So I do want to take a moment just to clarify and distinguish between what we're calling system models and what others treat as concept maps. So, first of all, concept maps are hierarchically constructed. They consist of tiers of components that are nested in some organized fashion that are arranged in different levels of hierarchy. System models do not rely on hierarchy. They might have hierarchy, but it's not essential to its structure. Secondly, the linkages or associations that we see in concept maps and models differ in the way that we think about them. As I mentioned in our models and system models, ideally those relationships are mechanistic in nature, that they have some kind of causal interaction or some relationship that explains how these two things are related to one another in terms of what they do. However, in concept maps, you're kind of free to make your own rules about what the nature of the associations are. And if you've looked at concept maps, you'll find that in some situations, there's no verbal articulation of the nature of the association. It's simply a mental association that someone connects two ideas together, and there doesn't have to be an explanation for the nature of that relationship. Third, the purpose of these two types of constructs are quite different. For concept maps, the objective is to map a domain of knowledge. So this relates to my fourth item here. So if you think about a student in a learning environment, a learning context, as they learn more and more concepts, as they become more proficient in a field, you expect that concept map to expand. And it can be very useful for documenting that kind of growth in students' thinking. However, with system models, the objective of the model is to describe the function of the system. So it's very process-based. So the nature of the growth was actually an unknown for us at the time that we began this. That was one of our leading research questions, and that's what I'm going to talk about here. So we wanted to know, how do system models grow as students accumulate knowledge and experience over time? Okay, in order to do that, we had to define a couple of metrics because we were interested in qualifying the nature of the model quality. So the two metrics that we operationalized for our research initially are model accuracy, and the way that we did that is we evaluated the correctness of the propositions that were constituent in students' models, and we computed an average correctness. And the second metric that we used was complexity. And different authors and different network analytics approaches calculate complexity in different ways, and we converge on an index called Web-like causality index, which just measures a degree of the interconnectedness of the components of the model. So that's good enough for now. So if we think about these, I want to talk to you a little bit about our hypotheses going forward. If we think about how these things might change over time, if we're looking at the relationships between complexity and correctness, one option is that both might increase over time. And that was actually kind of our thinking going in. That was our primary hypothesis, that both would increase over time. And we thought that that would be a reflection of improved learning. So the students are becoming more correct and they're interconnecting their concepts to a greater degree. That sounds good to us. We recognize that another possibility is that you could have a reversal of that, that maybe they start out high on both of those indexes and over time both regress. We would consider that a sign that we were doing something very wrong in the classroom, and we call this regression. There are some other options as well. So one would be that the students start out with a lower level of correctness, so over time correctness increases, so in this case we're moving the vector up to the left, but complexity is going down. So what do you think that that's an index of, or that's a measure of? They're becoming more clear. Someone said clarification, efficiency. So we call that parsimony. The models are becoming more efficient. And then the opposite of that, where we increase complexity but correctness goes down. Now, what do you think of when you see that? Yeah, exactly. So Andy Anderson is a leading education researcher at MSU, and he calls this procedural display. So that's the technical term. We call it shotgunning. It's when they throw everything in the pot, and you just hope something sticks. Okay, so what did we see? So the next graph is actually from the paper that described the outcomes of this project. We looked at 600 students across 3 sections of the same introductory bio class taught in exactly the same fashion among a collaborating group of instructors. And we documented the change in trajectory of each of the indexes over time. So consider in this case that the x-axis is our time axis, And what we see is that correctness does in fact increase significantly in the first part. This is about the first half of the semester. Correctness of models goes up significantly, and it continues to go up, but not in a statistically significant fashion. If we look at complexity, on the other hand, complexity takes a big increase early in the semester. So we have a lot of complexity increases going on. And in fact, what's really happening here is that these early models, students tend to create very linear models. They're not thinking about connections, they're thinking about a flow chart or a pathway. So complexity goes up quite a bit, and then it actually tapers off. So it actually goes down a bit. Given those different patterns that we just discussed, which one is this consistent with? This is parsimony. So we were able to fill in the rest of that table by indicating that over time, what we've observed in the classroom is that as students become more proficient in modeling and their content knowledge increases, we see a progression toward parsimony. So now we can add that to how we distinguish between concept maps and conceptual models. That's all I'm going to say in terms of the research, but I'll tell you some of the things that we're working on now, and then we can pick these up in the discussion if you care to discuss these further. We're interested in defining and finding other network metrics. I mean, network sciences has lots of different metrics that they use for explaining the nature and qualities of different networks. So we're interested in adapting those networks to students' models in order to see if those metrics can help inform us about the nature of learning over time, as the complexity and correctness indices did. We're also, I'm in the process of putting together this manuscript at this moment about looking at the alignment between the constituent components of students' models with paired narratives. So they're asked a single question, they construct a model, and they write an essay adjacent to it with the idea that these are both reflecting the same thing. And so our research is looking at the extent of equivalence between those two representations. I also have a graduate student who's defending next week. We're not ready. Which is, and he's interested in characterizing how students approach different modeling tasks. So depending on the nature of the context of the modeling task, the purpose, and the audience to whom it serves, students engage in a particular suite of strategies that differ among these different situations. And then finally, I have a postdoc, and we have this manuscript halfway done, which is looking at how do students perceive the purpose and value of scientific models. So I'm going to close with this because I was asked to speak to what are the resources needed and the barriers to entry into this particular approach. Well, this is what you don't even need the clicker. You just need the pen and paper and willing students. So that's the resource need there. The barrier to entry, I think, is fear, potentially, and having a plan. But I think that this is a really low bar way of integrating modeling into a classroom. It does take a little bit of time and coordination, and I'm happy to talk about specific strategies both here and in the workshop later. So I'm doing one of the first session of workshops where we'll talk about tools and tips and techniques that can help reduce those barriers to implementation. And I am now going to pass off to Rebecca.
Thank you. And so I'm going to take this one step further. I started in many ways, as Tammy described, with a classroom, with integrating models into pieces of what I was doing as forms of assessment, and then sort of slowly moved into the idea that this practice of modeling would form sort of the basis of practice in the classroom. So it actually is part of instruction, it's part of assessment, it's part of learning, it's part and parcel of the whole thing. It's introduced at the beginning of the class, and it's followed throughout the course. And so my course was focused on ecosystems specifically. We do talk about food systems as part of that, but the course that I'm going to talk about more broadly is ecosystems. So some of the examples are going to focus on that. And I had begun with the idea that a conceptual representation, something like SBF, was particularly important for learning. I had done various approaches to modeling in the classroom, especially with the idea of how to capture that complexity of systems, and found that it was really difficult, number one, to teach, number two, to assess, without helping the students sort of develop a kind of a space in their mind where they could attach that information. And so that's where I really sought a conceptual representation, which is basically an organizing framework for information. And so I had worked with colleagues at Rutgers, colleagues at Georgia Tech, the same colleagues that Tammy had, and began with this notion of SBF, structure, behavior, function, as a way to teach and to help students sort of hang their knowledge in their brains, kind of a categorical filing system, something like that. And in the work that we were doing at the time, we were also trying to help educators take what we were doing and then also teach that. And so we found it was really difficult to use the terms SBF and then with people who were ultimately going to take what we were doing and then go and teach it to somebody else. There was just too many sort of pathways for conflations of terms. The idea that, for example, this notion of function can be very teleological. The teachers that we had been working with, some of them in secondary schools, some of them in community colleges, were talking about sort of the why the system works as being that function. And so it was becoming difficult, especially when we're talking about broader explanations in evolutionary biology and things like that, to really see the what and the why and have that align nicely with the term function. Also the idea of behavior, for a lot of folks, especially in the biological sciences, really meant sort of something an organism did. And so the idea that there's a system behavior was really difficult for some of our educators to then take that and work with that. The other issue that we found was sort of the ordering of the terms, the idea that SBF, that structure came first. I think really some of the data that we gathered suggested that they were really focusing on that context, right? So if we were talking about a particular system or a particular farm or any place, the learners sort of began to kind of embed their idea on that place only. So when we asked them, okay, now let's go to another pond, let's go to another field, let's go to some crops in Africa versus the US or something like that, we found that our learners were really struggling to apply that same system framework. And so we did a little bit of playing around with the order of the terms as well. And we also found that there was some difficulty with the learners really working towards these kind of static linear stories, which is true of systems thinking at large, that we as humans enjoy kind of a series of events to explain how and why things happen. And so to have individuals in our classrooms sort of talk about things like what happens or some of the impacts of climate change or something like that, they would sort of say this and then this and then this and then this, and it's kind of a situation where all these things are happening at once. And so the idea of using a model to accompany this conceptual representation to help move them away from this kind of reliance on these terms and then this and then this and then this, to try to get them to kind of embed all these things happening at once and then to work them back out to their written explanations. And so, and then the last thing we really noticed was a huge reliance on visible evidence, what we could see, right? And so this idea of emerging properties out of systems, the idea that there are some of these indirect effects, things like that, was going sort of entirely underappreciated. So we really wanted to focus on that mechanism, on what was sort of underlying some of what we were seeing, to help them understand that there are things that we cannot see that still exist within systems. So all of that being said, our conceptual representation moved from SBF to PMC-2E, and I chose this for a number of reasons. So some people have worked with me have known that the -2E is particularly important, but it was something that doesn't flow off the tongue. It's not something easily memorized, and that's okay, because we didn't really want our learners associating it with anything else they'd thought about. So they're walking into this college classroom, they're seeing these terms, and they're thinking very little about it. I put it on the wall of the classroom. I take it in every time I go back into the class. We put it up. It's not something they have to memorize. They see it. It's on the top of their papers, everything. So they're given PMC2E, remember, PMC2E. And so what it stands for, they do have to remember. And that P is that overall pattern or phenomena they're trying to explain, which very much aligns to what Tammy explained with the F, right? But we're calling it pattern, or the thing that warrants explanation in that system. We do this so that they won't give us everything they possibly know about that system. So if we are talking about the climate system, for example, I mean, what does that even mean? It's huge. There's lots of elements. They will just put Earth, Sun, they'll put everything they can think of in that, and it's just not helpful for their thinking. And it's also, you'll get one student talking about this, another student talking about that if you're trying to get them to collaborate. So let's just disband with that. We often give them the P, like this is the pattern that warrants explanation. And then we move, and this is where that switch happens. And we've collected a fair bit of evidence to suggest that this is particularly important. This notion of sort of the what could have happened, what are the mechanisms that we think are likely in this situation? Let's think about that first before we start thinking about the parts and pieces in the situation. So the M aligns with the B, but in this case it would be sort of FBS instead of SBF. And doing that just to bring the learners back to the idea that we cannot forget about those underlying causal elements. And then the C are the components, are the structures that aligns very closely to what Tammy already introduced. So let's walk through a very simple example. This is an example that I do and use in my class because we have a big campus pond right outside the window, so we can look and there's big fish kill, sort of what has happened, why have the fish died? And so then we give that. That's the phenomena, is dead fish. This is the pattern. This is what warrants explanation in the system. And so then, I don't know where I'm pointing this to, there we go. And so then the thing that we want them to say, that we really want our learners in this situation to say is, what could have happened before they go out and say, oh, they were poisoned. You know, the first explanation that comes to mind, and then they're done, right? We know that students do this over and over again. No, we want to think of multiple plausible explanations at the outset. So what could have happened, and that will allow them to then begin to think about the mechanisms that they came to the table already knowing, right? And then again, that alignment between evolution and genetics and these different pieces, let's bring them together. And so they can begin to name starvation, not enough oxygen, all these things that they know could, even if they've never even met a fish, which most of them haven't, what could kill anything, right? You're living beings, you have some sense of that. Start to lay out some of those ideas. And then we can go back to what's plausible in that scenario. And then we can begin to think about the structures and the pieces that are there. And so that step, I argue, is particularly important because if they're going to look at a novel ecosystem, you know, they're going to then have to begin this process, again, of what could have happened and what's plausible here. And we know experts do this. We know that when expert ecologists or plant biologists, right, look at a certain system or look at crops or things like that, it's like they're often thinking about primary productivity. It's like the thing that's often in their minds when they look at the system, right? And that's true across systems. It's something that we know is going to be particularly important. They know to approach it with that. A novice learner will look at that and say, ooh, there's, you know, this kind of plant. Ooh, that looks tropical. There's that kind of plant. So the idea of like biomes in school, which almost drives me nuts, that, right, they teach that over and over again, these different biomes. It's almost reinforcing the idea of what's different about everywhere and forget that what's common about these systems. So then to build the PMC2E model, you could start with your parts, right? And so they will, fish, dead, water, they'll name anything. And that's fine at the outset. We want this to start operating as a system. So pretty soon, they're going to start adding components or adding pieces to that system that then we want to help them organize to get this in a working order to explain something that's dynamic. And so we begin to help them by saying, okay, maybe bad is a property of odor, or maybe bad odor is a property of water, right? And so maybe it's akin to dividing up some of these propositions or dividing up these smaller units and beginning to organize them together. We know that fish, there are many, there are dead, but what are the relevant parts? How do we work with those? And then, again, what are some of the other pieces that we're not seeing that we need to be thinking about to drive some of the plausible explanations that you may or may not have? And then we begin to draw those lines, those relationships between them, and how that might work. And then the 2E, right? We have an explanation. We are supporting that explanation with evidence. And that's tough, right? We know this is tough for all of our students. How do we get them to take these different pieces of things that they know, they don't even know where they knew it from often, and place it into this model? And so what we've then taken with that knowledge, which is very much pen and paper in the classroom, and moved it to a computer system where I could help them keep track of the 2E, keep track of what is that phenomena they're trying to represent, what is the explanation, you know, if their starvation killed the fish, that's your plausible, most plausible explanation. What is the evidence? Sometimes it can even say textbook, or, you know, I just thought of it, or I have no idea why I know this. It could be wrong. And so to begin to put that there, and then to begin to put in properties and separate them, and to give them the chance, the benefit as we talk about the positive and negative aspects of using something like this, the real benefit in this is that they can revise without necessarily trying to erase or using a new sheet of paper. So though they love paper too, sometimes it gets hard to really get them, they sometimes overcommit to something because it's like, well, I don't want to rewrite my model, you know, and it's like, no, in this case, it makes it a little easier to add and take things away, and then to constantly keep track. For every line drawn, you have to put a note. For every piece, and then to begin to organize your pieces, maybe into those, again, those propositions by looking at the colors. So I'm just going to give you a little bit of data, a little example from a course, and then Stephen will come up and show what he's been working on with his students. And so basically, we did do some drawing tasks, and we did some computer tasks, some models, and the real focus on this was these tools, but in this PMC 2E, conceptual representation rich kind of classroom experience, that we would start moving them to, the word models is missing, to more mechanistic explanatory models. And so just to give you a sense, the course layout was really 14 weeks, a semester system, pretty typical. They had various assignments. These were the various ideas that we talked about, big ideas. And that really, creating a course like this really forced me to start thinking about what are the big ideas I'm trying to get across and why. So it really helped me reorganize my own instruction such that I made sure I was really hitting those big ideas. And I sort of quit running out of time at the end of the semester where I was like, oh shit, we didn't cover this or that or the other thing. This organizational scheme really helped me. And then some of these were the drawings and the eco models. And I don't have a lot of time to explain some of the difference between drawing and computer models, but we've talked about this, Tammy, Stephen, and I, quite a bit, and we can talk about that later if you'd like. And so then, again, the data source, and some of it they were doing for homework, some of it they're doing in the classroom. What I love about the computer models is, again, they could be doing it at home and I could be assessing it in real time back and forth with them. But to give you an idea, because assessment is important, we can then take these models and sort of code them or grade them or whatever you want to call them for what it is we do in a classroom, and help identify if students were getting the main points, what they were missing. And so in boxes, you're seeing some of these bigger phenomena, some of these bigger patterns, and then we're pointing to, in some of the boxes, I said it wrong, we're looking at some of the bigger mechanisms. Here we're pointing at some of the major phenomena. The arrows are pointing to the phenomena. There we go. I can't see anything on this. I'm not going to put you in that. The arrow is really talking about this dead zone, the mechanisms, and then some of those parts. And just example of another model, and this is talking about sort of global temperature change as something they're trying to explain, and then looking at mechanisms like greenhouse effect, looking at mitigation in this context. And so one of the things, just to give you a sense of those outcomes, is that we did see a change pre to post, and we saw a change also. Another feature we added to this was having them work together as a group after doing individual models, so allowing for a little bit of collaboration. And so this was a small class, so it was a great class to kind of start embedding this kind of thing into it. So that's why you're seeing small numbers of students, but you're seeing at least an increase in the number of phenomena that they begin to represent. Pre-models were a little bit like everything I know. Post-models following the instruction were really oriented towards a particular something, which isn't surprising. I gave them the something. And so what's sad is that some of them didn't get it, but we work. And then the idea that we were seeing more mechanistic explanations. We were seeing students begin to add causal pieces together, which again, a lot of the models were lacking previously. It was a story. And then, but the idea that collaboration also changed things a bit for our students in that a number of them together, their models were more like expert models, right? They bring together a number of different ideas. I don't know if Stephen's going to talk about that today, but he certainly has data to show that the idea of bringing together these collaborative groups, I think, is particularly important, and this tool helps them. A modeling tool gives them something to work on, and so if your students are like mine, they hate collaboration. This gives them a little bit of a focus, something, a boundary where they can work together on it instead of leaving it wide open so that somebody could take over and everybody else complains, that kind of thing. And so we found that, and this was kind of separate in this case, I kind of kept it as a separate thing because it was kind of new. I didn't want to embed an entire course grade on something that I didn't know how it would go. So I just kind of kept that as, you tell students, right, it's worth points. My students will do it, even if it's worth like 1 point out of 100. And so everything else that they were doing that was a little more typical of assessment in the classroom, they did for the other like 95% of the points in the class. And so that I did that so that way I could look at how they were doing on models and how I might have graded them or assessed them on those models and compared that to maybe some more traditional assessments. And sure enough, they were highly correlated. So as well as they were doing in these models, was sort of reflected in many cases as well as they were doing in the class. So a lot of what I was measuring the models, I interpreted it as does align in many ways to what it was that I was also measuring in my assessments, and that to me was a good thing. And so, you know, the implications, maybe the take home from this idea is that we move from students who are a little less engaged to really, because they have sort of the boundaries, the rules, they're sort of embedded, week to week, is that sort of by the end of the semester, we began seeing more of this kind of thing, which I just love, where students just like, I'm going to do this, you know, this particular individual had a task in hand, and they were going to get it done and right, and they were going to create a model, in this case a pictorial model, but then use that. And so, again, I think throughout I really described some of the resource needed and barriers to entry. The tool, which I'm going to give a workshop on later after Tammy, is really just a simple app that can use on a phone or the computer. You don't have to download anything. When I give it to students, I just give them a few minutes to play, and they pretty much have it down. It's just click and drag. It's pretty simple. So that's nice because they don't complain about that. They complain if the internet's, you need internet because that's what it is online, so the internet's down. But then the conception, really got NCT, they can carry that and move it to paper. I think the idea is that in paper, sometimes they draw pictures, right? And it's like, that's a lovely mountain. However, I want you to draw concepts and ideas. So that's the only thing. On the computer, they don't have that luxury. But really, in terms of other barriers, it's really around time and comfort, which someone mentioned as well.
No, it's not. So I want to make sure we have time for discussion today. It's not a panel monologue, it's a panel discussion. So I may flow over some of the stuff I didn't want to say. So have a group discussion where we can learn some of the ways in which this stuff can be put into the context that you guys are working in. So Tammy and Rebecca come at this from a slightly different perspective than I do. I think they are really concerned and have done a really great job thinking about the learning that's happening in the classroom and trying to develop interventions in the classroom, the formal context that lead to systems thinking. I come at it from kind of an opposite view. I'm interested in systems thinking, but it's really more about building systems modeling tools that can be used by communities outside the classroom. And after doing that for a number of years, it seemed like it had some utility outside the classroom. So that's now what we're trying to do is move it over in the opposite direction. So I'm just going to give you a little idea about how I got into this or how I found pull that out of the closet and be proud to be a generalist. Yeah, I know, it sure is something. Yeah, I'm not a specialist, but I did, like what most of you start, you know, at least in my PhD training program, interested in becoming a specialist, and I was going to tackle issues related to fisheries science, marine ecology, and in particular I was interested in helping support the bycatch issue, which is a big problem in commercial fisheries, and you probably know bycatch is catching the species that you're not targeting for commercial fisheries, and that's because big nets are not targeted towards specific species, and long lines, the same type of thing. Commercial fishermen don't want bycatch either. They have to process that stuff, they have to deal with that. Environmental groups don't want it because it's a waste. I mean, they're just taking that biomass out of the ecosystem. And so when I started my PhD work at Rutgers, this was really what I was interested in focusing on. And like most fishery science, the way to solve this problem is to develop some sort of ecological model that helps us make better decisions about how to address this issue. And I worked with a team of great folks at NOAA, John Manderson and Josh Kohut, who's a physical oceanographer. And at the time, it was pretty novel to take physical ocean data and biological ocean data and put them together to figure out how marine habitat was changing for different fish. So what you're seeing here is, this is the mid-Atlantic in the Northeast, here's New Jersey and Long Island there, and this is the continental shelf, of course. And in this particular case, we were interested in reducing bycatch for butterfish, that's that little guy, in the loligo squid fishery. If you've ever had calamari, you've likely had loligo squid. And at this time, this is about 2010, 2011, fisheries management said, if you catch too many butterfish, we're going to shut down the loligo squid fishery. So there was a lot of incentive to work on this particular problem. And what you see here is our approach was to build this model and to find out where the bycatch species was so that the loligo fishermen could avoid those areas. And so this is on a daytime scale, and you can kind of see. So the darker red areas is where you're likely to find butterfish, and then the blue areas where you're not going to find butterfish. And this is it's a pretty cool model. We were kind of intoxicated with it. And we were going to take it to fisheries managers so that it could be used in decision making to solve their problem. And I'm not sure if you're familiar with how fisheries management works, but it's a fascinating system that's participatory. So commercial fishermen and recreational fishermen and scientists all get together at these different councils. There's 8 councils across the United States. And they have meetings about how to manage fisheries. And what's cool about these meetings is they're very diverse groups of people. You've got these decision makers that are part of the council that are assigned, usually they're the gubernatorial appointees. And then in the audience, you have all these different stakeholders. You've got these commercial fishermen, people who are interested in economic processing from the seafood industry, recreational fishermen and commercial fishermen and recreational fishermen are not at all alike in many ways. They're obviously fighting over the same resources. Environmental groups and scientists. And so we took our model in there and we said, lucky for you, we're going to solve your bycatch issue. And what we found out, and so at best, the model was met with skepticism, and at worst, it was met with hostility. And they were just like, you're wrong in so many ways. Let us explain why that is. And this was one of my big introductions, that everybody had a different mental idea, different mental model of the problem, and also represented a unique perspective on that problem. And so this got me thinking at the end of my PhD work, well, how can we take this knowledge diversity that exists across these groups and figure out ways in which they can be integrated and used to better understand the complexity of the problems that we're facing. Kate earlier talked about the idea of transdisciplinarity, and I think this is very much in line with sharing unique perspectives to get one model so that we can move forward. It may not be the right model, but it allows us to have a shared representation of what we do. So this was kind of my orientation into the field, and I began working on a software, a modeling software that allowed communities to have that discourse. And it was built around this artificial intelligence language called fuzzy cognitive mapping, maybe you've heard about it, which allows people to build concept maps, the ease of concept maps like we talked about, but you can also run scenarios on those concept maps to look at system state outcomes. So the idea is they're kind of bridging between system dynamics models that are highly parameterized and take, at least in the classroom setting, a lot of time to train students how to do it, and concept maps that are open and free form and very useful and very easy to use in the classroom. So this is hopefully a little bridge between those two things. The goals of the software to be able to represent and standardize knowledge. So Tammy talked about allowing kind of open form concept maps right at the beginning, and the difficulties of how do you assess when you have no limitations on it whatsoever. This was a way in which that information could be standardized so that one person's mental model can be compared to another. It is meant to be low barrier, very flexible, and so there's an ease of use in the modeling process. Because you can run scenarios, you can test hypotheses. You can see what the system state output or the function might be if you change different variables. And really, my overall interest in this is to understand the complexity of social ecological systems, which is something I cover a lot in my class. So here is a video, but I'm not going to show it for time so that we can have this conversation. But I will give you an idea of what the software looks like. So it's got a concept mapping interface where students can just define what the concepts are that are important to understand the problem, as we've talked about. And these relationships are linear relationships about increasing or decreasing. So in this case, component B, when it increases, it decreases C. And so students can represent the network structure of whatever problem it is they're modeling. The software translates these models into, into using network metrics based on the weights that students assign on those relationships. And so it automatically generates a view of which are the most important components, the most central components, which are the driving factors, which are the receiving factors. And it automatically generates a lot of information about the model as students put them together. And as I mentioned, you can increase or decrease any of the components that you represented to look at the system state output. And so we've had a lot of success, and we've been really fortunate that in Europe and in the United States, a lot of federal management agencies that are interested in increasing participation and fostering transdisciplinary research around sustainability. But it occurred to me, after I started teaching and trying to bring the context in which the computer and software has been used in the classroom, that we have the same problem, or at least I did, where I had an idea of kind of the complexity of the problem that I was representing, and students had a very different idea. So how do we foster that same kind of systems-based thinking in the classroom as we were trying to do with fisheries and other contexts? So right now we're trying to use the software and test it to see if we can promote learning feedbacks through systems-based modeling by kind of mimicking the scientific process, because most of the ecologists that I used to work with, they would kind of have a mental model of a problem in their heads. They would represent it on a computer and formalize those informal rules that were in their head, their hypothesis. They integrate it and they collect other data around that particular context, and through that process, they learn. They change their own mental model about whatever problem they're trying to address. So we're trying to promote those learning feedbacks. The other thing that I'm very interested in, and I think Tammy's leading the way in some of this research, is understanding learning trajectories over time from when students enter a context and they exit a context. What does a systems thinking trajectory or trajectories look like? And so you can imagine a situation in which students enter a context where at the beginning of the course, they're understanding things about plant growth, maybe farm dynamics as it relates to corn production, soil health, and that kind of thing. If you ask them a couple weeks later, after covering information about public health, they may add to this initial model, where does high fructose, and again, I'm a generalist, I don't want to hear about my model, but how it relates to diabetes and obesity and other things. And then by the end, we hope for a more complex view of the relationship between farm dynamics, public health, and maybe US policies. And what we can do as students progress and build multiple models over time is evaluate that, well, when they came in, the model will give you an idea of how many components there are, how many connections, feedbacks, that type of thing, but also qualitative measures. So at the beginning, the model represented that the biggest driving factor of the system was nitrogen deposition, and the most central were nitrogen, plant growth, and corn. And maybe at the end of the course, they have more components in their models, you would imagine they would, more connections between things, but what's driving the system at the end may be something like farm subsidies or policy. They realize the role that plays. and the most central may be things like incentives for commodity crops or what else. This goes back to, if you're interested in this idea about a continuum of systems thinking, Christina Stade has done some really interesting work. She really comes out of system dynamics a little bit, and so she uses concept models and simulation models over here when she describes it. I would suggest that you can use them iteratively as you go for both assessment and to promote different types of systems thinking. I'll skip over this so that we have some time to talk, but I've been giving students articles in class and just saying, read this article and represent it. And so here's one example from PNAS that was a very interesting article about climate change and how it impacts terrorism, and they collected data on this. Having students represent a highly uncertain system for which there is a little evidence, but it's still largely unknown, is something I'm very interested in, wrestling with those types of things. Then seeing how their models relate to function, and especially around sustainability, being able to use these models, the structure and the function, to identify leverage points for change. Where is a point in which we can steer the system into a preferred direction? And we have some ideas, I think, and Tammy and I are going to talk about this certainly during lunch, about what these trajectories might look like as far as how this concept maps we expect them to change. And one of the things that she's already mentioned is we think things like components are curvilinear, in where you interact with some kind of information, you build on it, but then you refine it down to a more expert, parsimonious understanding. And with that, I think we have a little time for the actual panel discussion.
Terrific, thank you. So I'm going to get started with one or two questions, but then we'll hope to you guys in the audience. And I think we have like 15 minutes for questions. So I guess I have so many of them, but one of my most important questions, I think, and hopefully audience members might be interested in this as well, is systems scale. So how do you figure out the boundaries? And then Kate Clancy this morning had a really important point about making sure there's communication between those scales. So how are you working with students to recognize that whatever boundary they choose, there's a whole other system around that that might actually change the question and the responses, and then figuring out ways to work on that communication between them? That's pretty tricky. So how do you guys deal with that?
Very briefly, hyperlinks. So that's where, again, sort of working with the computer is helpful, so that students can sort of indicate on the bottom of their model that this is where the other model goes. And so then you could sort of imagine them building a PDF, which I've done in a class, and so then they click on it, and then their other model shows up to have them see that that's within scale. Sometimes having different groups of students work at different scales, and then having them collaborate to build a scaled model. So we're constantly dealing with that issue and playing around with various tricks that the students are already familiar with, even in something as simple as Word. Or one group of students worked with Weebly, which is a free web software, so that way they could create a web image of just different scales as they moved in and out of the scale.
Yeah, I think that's one of the strengths of the computer-based modeling, is that you can dive into concepts, so they can be multi-dimensional, in the sense that the components, as you address them, you can talk about what scale they exist at and put in hyperlinks and links to other web pages, and so it kind of gives a structuring to diving in and out of different scales of the concept map.
As I hand this over to Tammy, I'm thinking we also use scissors and tape on their handwritten models too, so for that you can easily do a low-tech solution.
It's funny that we've actually never discussed this exact issue before, but I'm struck by the fact that we all use exactly the same language. So even though we're doing this on pen and paper, we talk about hyperlinks. So students will build different models or different parts of systems at different times. So for example, if one of the models that we focus on in the classroom is movement of carbon through an ecosystem, but you know that a component of that would be the process of respiration. So the students might have in their portfolio a model that they've done earlier in the course about cellular respiration and how carbon's moving in and out of the plant at the organismal level. And we talk about when you're building it at the ecosystem level, imagine that this component or this particular place in your model can be hyperlinked, and it takes you to this respiration model, or you can substitute that in. So I think that's funny that we all use hyperlinks as a way to explain it, even with paper. So.
That's great. Do we have questions from the audience? I'm going to have us mic for the folks in the virtual audience. I'm going to have you speak into the microphone.
What a great panel! Wow. I just wish I had heard you folks before I tried teaching system dynamics. It would have helped so much, your ideas about how you assess knowledge. One of the issues that is lingering for me, and I'm still thinking about Tom's presentation about Food Solutions New England, and then coming back to what you folks are talking about with assessing, where one of the purposes of Food Solutions New England is to basically change community members' mental models. And I am wondering what you can say about success in merging models. When you were looking at the bycatch, I was really struck with your picture of the different participants in the meeting and how some of them are thinking this is nonsense, and some of them are thinking, wow, if they only knew the real facts and how all this fits together, it would be so different. What about if you incorporate what Tom is bringing up about framing, the importance of framing? A lot of people in communities, when you go outside a classroom where you have some control and you can assess learning, but when you have an objective that might be, you know, a life or death objective, like how are we going to deal with climate change as a planet? How do you deal with the fact that for many people, they really aren't interested in changing their mental model? They want to reinforce that mental model, and regardless of what they hear from you, they are going to either discount you or just walk away with the bits that did reinforce their mental model and eliminate anything else. So if you think about framing and different ideas that people have, and actually in the classroom, this is relevant too, because some students are just really resistant to having the ideas that they've either learned from other classes about, say, the Green Revolution and how change happens and agricultural development. They don't want to hear your ideas about social movements and solidarity economies. They're just incorporating what reinforces what they already know. So maybe that's a kind of hairy question, but I'm interested in how you can apply this when you're engaging with communities.
So, well, that's a very good question. I don't know if I have a great answer. I would say that Rebecca and I have an NSF project that is engaging citizen science in local land management issues. And so in that particular case, we have a motivated group of individuals that are seeking change, and we allow them to collaboratively model, share their mental models, and then figure out an action plan. It's a research-based action plan based on that. And that's worked out very well. I've also done this in Flint, for example, and you've also there got a motivated community to understand how they're going to be impacted by the lead exposure and what solutions that they recommend from the community level. When doing it in more contentious, or if there's a lot of diversity in their mental models, it's a little bit more difficult. However, with FCM, the fuzzy cognitive mapping in particular, you can have everyone develop their mental model and then aggregate them. So everyone can see where they fit within this larger model, and for discussion, for debate about, you know, what is a preferred direction for the system to move in, or a question about values. And so it allows you to look at knowledge kind of on a more neutral space next to everyone else. But we've been fortunate in most of our work that we're already working with motivated communities that are seeking change, and then it's been relatively easy to use these to facilitate that understanding.
In the cases where I've had people maybe who have different impressions about what they'd like to see as an outcome of a group meeting for whatever reason, or where they actually have entirely different agendas. I have used Mental Modeler, the tool that Stephen talked about, which has this great ability to kind of merge models. I've used it in the classroom as well as students come to the table with different ideas. I will use it so that they generate their model. We talk about sort of rules ahead of time, some things that we don't say that you're going to need to change your agenda or your hope for the outcome, but this is our process. And so we agree on the process ahead of time. We take the models, actually, and I will take away the arrows in the mental modeler, so I merge everybody's terms. And so now everybody in the room has their terms that they felt should be part of the model on that model first. Then we have a process of just eliminating duplication. So that way we can get people using the same words to mean the same thing, which is again, viewing that knowledge in an objective way first and foremost, saying, I know you think this, but we're not at that stage yet, but we'll get there. And then we begin to draw the connections, we begin to describe a system or a scenario as is, or why, as we think it is, and we begin to talk about why we're viewing it differently before we even move to which state or which outcome we want to see. And then we begin to play with the model to say, okay, if this is what we wanted to maximize, then this might be. If that's what we wanted to maximize, then that might be. And so then what we often end up doing in the two cases where the groups have been more contentious is we end up with like 2 or 3 different scenarios that they can fight about, which makes it a lot easier than fighting about everything under the sun. And so then we can decide on a process by which that decision will be made. Sometimes there isn't a need. In one case, there wasn't a need. We disagree. These are the 3 things. At least we now are closer to understanding each other. In another case where a decision had to be made, it became, okay, who has the power in this situation? Who will ultimately be making the decision? How will that work? And so, again, narrowing it down so that you get people arguing about pointed, specific things tends to work a little better. We can remove the emotional aspects of the argument. And so in class, when I pick a contentious topic so they can begin to practice doing that, it has worked really nicely. I do use Mental Modeler versus the tool I talked about, so that way we can talk about outcomes and they can look at those graphs and begin to compare. But that's how we do that. I don't know if you deal with contentious issues in your classes. In that way.
Right here. Thank you again for a great discussion. So I'm really interested in that concept of complexity going up and back down, and I actually think that relates to how do you connect it to the community, and what do they take with them, and how do they end up using this, and does that help them to be able to put what they learned into practice, that up and down of complexity?
Well, I can only speak from the perspective of the classroom, so if they probably have something to contribute in terms of taking it beyond the classroom, but we were really surprised by that outcome. It wasn't necessarily what we expected, but now what that has afforded us is that we can be very upfront with the students going in. So now we train fundamentally differently in view of that finding. So we encourage the students earlier on to be thinking very critically about their model, and much of that comes through shared collaborative modeling. Students will construct a model on their own, bring it into the classroom, and I'll have everybody put it together on the table. And they have to think about what are the priority relationships and the priority structures in here, and what is extraneous information. And we also try to use a little bit of that teaching moment to have them reflect on other ways that they communicate and to apply the same principles. So for example, when you're writing an essay or you're writing a written explanation, do you find yourself doing the same thing here? Is there extraneous information that's muddying what it is that you're really trying to communicate? So can you provide some clarity? So we found that that's pretty helpful, and this is an example of using research findings to inform instruction.
That's exactly, we have found this with Eco-Modeler too. I didn't mention that, but the same kind of trajectory over the course of an issue. We've certainly found it with our community members that we've worked with as well, that same sort of refinement Turns out that when you want to make a decision, sometimes having the most important driving variables be the ones that influence your decision is a far better idea. And so having some of that fuzzy logic mathematics behind it to say pointedly, let's look at this, refinement. And so I often will compare to in the classroom student models to expert models, showing them that they are indeed more refined. It's just easier to think, it's easier to reason, it's easier to move. And so we use that as a teachable moment too, and I use it to guide where my community groups are when we're moving forward. We've had some groups where there's just a gajillion terms still on that model. They just haven't gotten to the heart of the matter yet. So that's part of something that I use as a guide, but that same kind of phenomenon. And that idea of procedural display, when you really start to unpack it, you do see that people are sometimes putting terms up because they think they should, or they're sort of imitating what they've heard somewhere, and they're not really, it's not really embedded in their reasoning. So we really try to get at, we don't reason with a million points at once. We reason with very few. What are those points we need to be reasoning with for that outcome?
And I would just point to some empirical data we have from 250 recreational fishermen in Germany, as you do. And we look at how their mental model about the lake systems that they manage correlate with their experience with the lake, their level of expertise, and also policy support. And there it appears to be a very clear tipping point or threshold at which people's ideas change enough to where their preferences for management also changes. And so that's something we're interested in looking at more.
So Julie, we're going to take your question. Can you just speak it out loud?
Yeah, I can do that, yep. So thank you all for your presentations first. It's a treasure trove of ideas. I'm wondering how students enjoy each of the tools, using each of the tools that you presented. You know, I've seen situations where you bring this great tool and you know they're learning, you know if they do it right, they're going to learn from it, but they hate it, you know, and they all, I'm not saying any of them hate it at all, but you know, that general sense of discontent gets into the classroom, we're in trouble. And so what do you do to make them or help them appreciate what you're bringing to them? Do they like?
So for the web audience, I think I'm just going to repeat really quickly and not as eloquently or passionately. Do they hear them? Never mind. Perfect.
Oh, great.
They hate them. But let me qualify that. They particularly hate them at the beginning of the semester. And there does seem to be an evolution that happens during the class. So as the students become acquainted with the technique and with the approach, and the recognition that often what we're modeling is the same thing over and over again, but applying it to different contexts, it takes a while for them to realize that that's actually what we're doing. We do a variety of different kinds of models, but one type of model in particular, we're trying to get them to really think about how all these biological concepts relate to one another and can be applied to multiple different contexts. They're universal principles. And so the moment in the class when I know that we're where we need to be is when the students say, haven't we done this 100 times already? It's like, yes, thank goodness you finally figured it out. But there does seem to be that evolution. They hate them very much at the beginning. They go through a transition period and then they become much more happy with them as time goes by. The other distinction that is very predictable in the classroom, I teach for majors, and non-majors are much more receptive to this approach. And when I have certain types of students in the class, I can always reliably predict that they're going to love models. And those students are engineers, anyone with an artistic interest or background, and students that feel that they can't communicate through words. So those students, now the gunner, going for the 4.0 GPA, I'm going to med school, come hell or high water, they hate these. Because this is taking them completely out of their multiple choice comfort zone, so they don't like them. But they come around, most do.
And I think I would echo some of that, as well as add that while they do, we are changing the rules of the game, right? And so generally, no matter what you do, when you change the rules of the game, people who really do well at that game are just not going to like that. And so I am upfront with them at the beginning. I give them the chance to actually drop my class if they must and find somebody else who teaches the same kind of thing, however, with a different approach. But so that way I can say, hey, you signed on, like I gave you a chance. But for the most part of it is trust that, they almost in many ways don't mind as long as you still promise them their A. And so, so I can kind of get them along by saying this will in no way, and I have data to suggest this will in no way hurt your A. And so that helps as well. But another group of students who do seem to appreciate this too are students who are struggling. And so students who traditionally have not done as well through other modes, who haven't mastered the game, a new game where they can achieve suddenly becomes a lot more motivating. And so that is also well appreciated. When it comes, but that's the rules of the game, that's the PMC, that's the idea that we're modeling. When it comes moving between the paper and the computer, everyone has their little preferences, but by and large, the students don't mind at all. They like the tool because it allows them to not have to rewrite something. As long as internet's working wherever I'm teaching, you know, if technology fails, they're frustrated with it like anybody else. But, and then for those who are really on board, when I increase, the complexity increases as we go on. We start with the paper, we move to eco-modeler, they become used to that mode. Then we might move to mental modeler depending on the course. They become more used to that mode. Giving them a time to just hand it to them and say play, allowing them 5 minutes before you even say a word, often helps them to just become a little more comfortable with the app or with the mode. So it's got to be, in my mind, very slowly introduced to them. But establishing that trust and saying, you're not going to fail, don't panic, this is something different. But I've had students at the end of the semester just say, thinking is hard, you encouraged us to do more of it than most classes, you know. But you're nice, that kind of thing. So by and large, the difference between the technology and paper, not a problem for my students traditionally, as long as they work, and these do work, which is nice. But changing the rules of the game, they are not usually on board entirely until you build that in.
Yeah, it's interesting to hear that. I think Tammy, I've had the exact same experience that Tammy has, where there are different personality types, and they all come at it from a slightly, some of them really enjoy it, and some of them not so much, especially those students that want the right answer, especially for the types of systems that we're modeling.
Yeah. I've had one student say to me, though, that it changed his life entirely, and he models everything now. So you might have that moment where you just opened up somebody's life.
I just wanted to add on one thing that Rebecca said. It actually reminded me, in the paper that we report the long-term outcomes, we also have data that shows differential achievement for students among different tritiles. And what we find is that across all tritiles of achievement, high performers, mid, and low performers, that they all increase their model performance proficiency. However, those that are in the lowest tritile make the greatest relative gains. So there's actually a little bit of that closure of the gap.
Great. Well, please join me in thanking this terrific panel.